Okay, imagine this. You're trying to carve something really intricate, maybe super detailed, but your whole setup is, well, let's just say it's a bit wobbly.
Yeah, like trying to write calligraphy during an earthquake. Not ideal.
Exactly. And that's kind of the challenge we're digging into today. We're looking at machining complex parts on CNC lathes, but under unstable conditions.
It's a huge issue. You get vibrations right, and that just ruins the surface finish.
Totally. Or your tools wear out way too fast. Worst case, they even break.
Yeah, been there.
So if you've ever fought with a machine setup that wasn't quite rigid enough, or maybe you just appreciate the incredible precision that modern manufacturing needs, then this deep dive is for you.
And it's fascinating, isn't it? This constant push for more complex parts, butting up against the actual physics of cutting metal. Instability is just inherent sometimes.
It really is. It hits quality, it hits efficiency, everything. So our mission, basically, is to explore how the industry is tackling these shaky situations. We're zooming in on some really interesting cutting tool tech from Iscar.
Right. I saw the source material in an article looking at Iscar's approach. They're talking advanced tool geometries, anti-vibration systems.
Yeah, and cooling methods, optimizing the parameters, the whole package.
It makes sense. If you can get a handle on stability, especially as parts get trickier and materials get tougher, that's a big advantage.
Absolutely. So let's get right into it. The core problem: instability and cutting forces. Why are they such a massive headache for high-accuracy, complex parts?
Well, think about the forces involved. Even tiny forces, when you're cutting metal, can cause big problems if the workpiece or the tool isn't held perfectly still.
It's like that jelly analogy again, right? A little wobble goes a long way.
Precisely. And it sets off a chain reaction. The tool doesn't cut cleanly, it sort of chatters.
And that leads to
vibrations, first off, everywhere. In the part, the tool, maybe the machine itself.
Okay.
Those vibrations mean the part gets deformed slightly. It won't match the blueprint exactly.
Right, tolerances go out the window.
Exactly. And the tool itself, it wears down much faster because it's hammering away instead of slicing smoothly.
So reduced tool life. What about the finish?
Forget a nice smooth finish. You'll likely get chatter marks, sort of a rough, uneven texture. It all adds up to inaccuracies.
Sounds like a recipe for scrap parts and lost time. And I guess it's even worse for certain types of parts.
Oh, definitely. The article mentions parts with thin walls, for instance. They're just naturally more flexible, more prone to vibrate.
Makes sense. Like a tuning fork.
Kind of, yeah. Or parts with high aspect ratios, long, skinny things. Any instability gets amplified way out at the end.
Okay.
And then you have materials that aren't uniform, non-homogeneous ones. The tool hits a hard spot, then a soft spot. The cutting forces change, and that can kick off vibrations too.
Right. Unpredictable. Okay, so we have these tricky parts, and the cutting forces are just waiting to cause trouble. How is Iscar fighting back with tool geometry? How does the shape make a difference?
Well, Iscar, being part of IMC Group, they've really focused on that point of contact, the cutting edge, trying to minimize the force generated right there.
And one example is the Logic 4 turn.
Yep, Logic 4 turn. It's got 4 cutting edges, which is good for tool life, obviously. But the really key thing for stability is its geometry, specifically positive rake angles.
Positive rake angles. Okay, break that down for us. What does that mean practically?
Okay, think about the angle of the cutting face as it meets the material. A positive rake means it's angled to sort of lift the chip away. It shears the metal cleanly.
Ah, like using a really sharp knife at an angle.
Exactly. It's more of a slicing action, less of a blunt pushing or plowing action.
Okay.
And that slicing action requires less force. Less force pushing against the workpiece means
less chance of it vibrating. Got it.
Bingo. Less force, less vibration, more stability.
And the article compares this directly to the older CNMG inserts with negative rakes, right? Why are those worse in unstable setups?
Well, those negative rake inserts, they're strong, but they basically have to push harder to cut the material.
Okay.
In a really rigid, heavy-duty setup, that might be fine. But if things are a bit unstable, that extra force just makes the vibrations worse. It amplifies the problem.
So Logic 4 turn, with its positive rake, just cuts more.
Yeah.
Gently. More efficiently.
You could say that. It leads to a cleaner cut, less force, better stability, and usually a better surface finish as a result. It's a noticeable difference in these tricky situations.
That's a really clear benefit. Smarter shape, less wobble. Okay, now Iscar also has the Logic 6 turn, 6 edges. Sounds efficient. How does that one help with unstable parts?
So Logic 6 turn builds on that same idea. It's a triangular insert, but cleverly designed to give you 6 positive cutting edges.
6.
Yeah, more edges per insert means better economy, obviously. But again, the geometry itself is optimized to really minimize vibrations, especially on those less stable parts we talked about.
And a big plus mention was compatibility with standard TNMG tool holders. This seems really practical.
Oh, it's huge. It means shops can try these advanced inserts without needing a whole new set of holders. It's an easy upgrade path.
Less disruption, lower initial cost.
Exactly. And because of that advanced geometry, you get that smooth cutting action, reduced forces, better finish. It's a really good option for anyone dealing with parts prone to vibration, maybe using lighter machines, or just where the setup isn't perfectly rigid.
Okay, so clever tool shapes are tackling the forces head on. But sometimes vibrations are just stubborn. They still happen. That's where the whisper line comes in.
That's right. The whisper line is Iscar's anti-vibration system. Think of it as actively fighting back against the shakes.
How does it work? Is it in the tool itself?
It's actually in the tool holder, the part that holds the cutting insert. These holders have internal damping mechanisms.
Damping mechanisms, like shock absorbers.
That's a great way to put it. Yeah, they have a tuned mass inside that's designed to vibrate at a phase with the machining vibrations. So when the tool starts to chatter or vibrate at a certain frequency, this internal mass moves in opposition, effectively canceling out or drastically reducing those oscillations.
Well, that's clever. Active cancellation right in the holder.
It really is. And it's particularly effective in situations where you have a long tool overhang, when the tool sticks out really far from the holder.
Right, that acts like a lever, making vibrations worse.
Exactly. Whisperline helps tame that chatter, that high-frequency buzz that ruins finishes. Even if the machine tool itself isn't the most rigid thing in the world, this can make a huge difference to your surface quality and dimensional accuracy.
So you could potentially hit tighter tolerances than you thought possible on existing equipment.
We've seen that happen, yeah. The article really drives home how it boosts performance, productivity, and even tool life when you're stuck with unstable conditions. It's quite impressive.
Sounds like a real game changer for those tough, long-reach jobs. Okay, so we've got smart tools and anti-vibration holders. The article also mentioned cooling and parameters. Seems basic, but still vital.
Oh, absolutely critical. You can have the best tools, the best holders, but if you don't manage heat and run the right speeds and feeds, you'll still have problems.
So cooling first. How does that play into stability?
Well, effective cooling, especially when it's delivered right to the cutting edge through internal channels in the tool, that pulls heat away super fast.
And less heat means?
Less chance of the workpiece distorting or warping due to temperature changes. Thermal stability is crucial for accuracy. Plus, it helps the tool last longer, too.
Makes sense. Keep things cool, keep things stable. And optimizing parameters, what are we talking about there? Speed, feed?
Exactly. Cutting speed, depth of cut, feed rate. Finding the sweet spot, that perfect combination for your specific setup and material that can massively impact stability.
It's not just set it and forget it.
Not for these challenging jobs, no. You need to dial it in. And the article even touches on real-time monitoring systems.
Using sensors to watch the cut as it happens.
Yeah, systems that provide feedback, allowing operators or even the machine itself to make small adjustments on the fly to keep things running smoothly and minimize vibrations if conditions start to change. It's getting quite sophisticated.
Very cool. Okay, so we've covered a lot of ground here. Smart tools like Logic 4 turn, Logic 6 turn reducing force, Whisperline actively damping vibrations, good cooling managing heat, and careful parameter optimization. If you put it all together, what's the big picture?
The big picture is that you can successfully machine complex parts even when the conditions aren't perfect. It's not just about fighting physics anymore.
There are tools and strategies now.
Exactly. By being smart about it, choosing tools designed for low force, using anti-vibration systems, keeping things cool, optimizing the process, manufacturers can get much better, much more consistent results.
So boiling it all down, for someone listening who's maybe facing these exact problems, what's the key message?
I'd say the main takeaway is that solutions exist and they work. Don't just accept vibrations and poor finishes as inevitable. Look into these advanced tool geometries, especially positive rake ones. They really do cut forces. Consider anti-vibration holders like Whisperline if chatter is a persistent issue, especially with long overhangs. Don't neglect cooling. Get it right to the edge.
Yeah.
And really spend time optimizing those cutting parameters.
And the payoff is?
Better surface finish, definitely. Longer tool life, which saves money. And overall, much more stable, predictable machining. That means higher productivity and better quality parts consistently.
Fantastic. So a quick wrap up. Tackling unstable machining isn't about one magic bullet. It's a combined approach. Minimizing force with smart tool shapes, killing vibrations with things like whisperline, controlling heat via cooling, and fine-tuning the process parameters. Understanding this stuff gives you a real leg up in overcoming those tricky machining jobs.
And, that actually brings up an interesting thought to leave you with. Think about these principles we've discussed. Managing instability, controlling forces, using smart design, active damping, optimizing processes.
Yeah.
How could these ideas apply elsewhere, outside of machining? Think about other areas of engineering, or maybe even challenges in everyday life where you need precision and stability under less than ideal conditions. Are there parallels?
That's a really interesting question. Applying precision principles more broadly. Definitely something to think about.